because you had a presentation. That's your excuse. Yeah, good luck. All right, let's get started with lecture 8. So we're going to move into chapter 3, and part of this is going to be for your exam. I might include it, since you have not started the assignment, I might include it as part of your assignment. Since you have not started your assignment, I might include it as part of your first assignment. Chapter 3, yeah. Will be part of your exam as well, yes. Partially. I think it's lecture 8, okay. Because you're not, have you started the assignment number 2? So if you're not started, then I can include more. Have you started, Leon? Huh? Okay. So if you haven't started, yeah. I told you guys that I've given you more than a week's time to do the assignment. There's a reason that much time is given. More than a week? No. I put it up on Monday. And the assignment is due. Yes, the assignment is due on Wednesday, which makes it 10 days. So you are not supposed, there is no excuse for not starting it for half the time, right? And all of you chose this time, 11 to 12, so that you could make it in time. I was only, Antoine was there outside when I came. Nobody else was here. Okay. All right, let's look at some definitions for, this would be start of chapter 3. Please get started on assignment 2, okay? This will not be part of your exam, but if you get started, what's going to happen is you will not have enough. You should have started the assignment now, so you could have asked questions today and worked it over the weekend. Okay. Because if you do it over the weekend, you will not have much time to solve it after the weekend. How much time will you be left with? Tell me. Huh? That's not much. If you are stuck in the weekend, what are you going to do? You cannot really ask questions in the weekend, right? If you at least attempt a part of it, even initial part of it, you can ask questions and you can use the weekend to solve it. That's the reason there is a weekend in between. All right. So we'll look at some definitions. First one is, and if you have questions, you can stop by my office. Linear combination. your independence. simultaneous, Taneous, simultaneous first order differential equations with n variables. All right. So these are the definitions which are going to be relevant for this chapter. So let's discuss a little bit about what this chapter is supposed to do. So chapter 2 was about, what was chapter 2 about? What did we do about chapter 2? Huh? Right. So what was transfer function? How do you define transfer function? The ratio of output to input. Correct. But what we did was we looked at differential equations and took Laplace transform of those differential equations, right? Or system relationship, the Laplace transform of system relationship. What does Laplace transform? What does Laplace transform do? Correct. So Laplace transform did transfer the a time domain function, relationship in time domain to frequency domain. Now this one is, this chapter is called modeling. If I were to in time domain. So we are going to take a look at the differential equations, or we're going to take a look at deriving the system input-output relationship in a time domain, but not necessarily as differential equations, or not more than first order differential equations. Okay? Yes, welcome. Output equation, the algebraic equation that expresses the system. Here what we are going to do is we are going to take a nth order differential equation and convert it to n first order differential equations. See what I'm saying? Take an nth order differential equation and convert it to n first order differential equations. So if it's a second order differential equation, how many? Two first order differential equations. You'll have two first order differential equations. What is the advantage of doing that? It's easier to, more than easier to solve. you'll have a whole set of new solutions for that. So what we are trying to do is, this is the general representation of a we call this state space system, okay, or modeling in state space. Modeling in state space, modeling in time domain. Frequency domain is, see, as aerospace engineers, you should understand that frequency domain modeling applies only to linear time invariant systems. But frequency domain modeling, transfer function, applies only to linear time invariant systems. Linear time invariant, we have discussed this, right? However, as aerospace engineers, do you deal with linear time invariant systems? You rarely deal with linear time invariant systems, especially if you're going to put something in space. It's always going to be a time varying system. It's a linear time invariant system. Frequency domain applies to linear time, LTI systems, correct? But as aerospace engineers, your systems are always going to be non-linear, first of all, and they're going to be time varying. The system property is going to change as time progresses, correct? You can, but you'll be limited. If you're going to design something, you'll have to really linearize your non-linear system, and then have a frequency domain model for every significant variation of the system variable, right? If you have, for example, if you have a rocket going up, right? See, for a rocket, it's very difficult to do anything because the system property is varying very quickly, right? Do you realize that? The system property, the mass is varying very rapidly. So if you were to, let's say this is at time t1 and this is at time t2, right? You need model 1, model 2. You need to keep changing your model. You need to keep changing the input-output relationship. The input-output relationship keeps changing, and you need to apply the control laws, different control laws for as time changes, and you have to discretize it. You understand what discretizing is? So this is this a linear function or a non-linear function? Non-linear function, right? So if you T1, T2, T3, T4, what I'm going to do is between T0 and T1, I'm going to linearize this, okay? Which means we're going to assume this as a straight line for this. You go from T2, so we are going to again assume this as a straight line. You go this way. Now see, when you keep doing this, right. Right. So your approximating between times, you're approximating the function to be linear. But what you're going to do is you're going to lose the fidelity of the model. You understand fidelity? Accuracy. In a way, the accuracy. The fidelity means it is not an exact representation of what the actual dynamics are. Okay? So you're going to approximate between time slots. And so this, between T1 and T2, you have a time invariant system. You have a LTI system. Between T2 and T3, you have another version of the time invariant, but it's a different model here. You see it? So when you keep doing that, you approximate, and some of your estimates, for example, how much you need to fire, how much thrust you need to produce, may not be correct. So you have to deal with that. But your solution, you could choose something like this, something like state space modeling to develop a nonlinear model, a completely nonlinear model of your system. Although you cannot apply all the principles of what we are going to discuss, but this state space modeling can be applied directly to a nonlinear system, and you can develop a nonlinear model. Okay? Can a differential equation be nonlinear? What constitutes a nonlinearities? How do you figure out if it's nonlinear or not? Not necessarily the order. Huh? The order, yeah, actually order could be a nonlinearity. Nonlinearity could be order, cosine terms, sine terms. Cosine terms, sine terms will always do this, right? Whenever you have a cosine term of a variable, it's always going to add something like this. So it's going to be nonlinear, right? Exponential term, it's going to be nonlinear. If, for example, you remember this equation, if you've taken orbital mechanics, this is the two-body problem, right? Two-body problem statement. This is a nonlinear system. Nonlinear, it's because, see, this term makes it nonlinear. Okay? Not the mu. The variable, see, it has to be, mu cannot make it nonlinear because mu is a constant. Whenever you have a system, if it's multiplied by a constant, it will be throughout multiplied. If you have a linear system, what happens if you multiply? You're going to get this. It just is going to shift. It's not going to change the slope. Okay? This is a variable, right? So variable, this is also variable. The vector itself, the vector and the scalar. So this term is going to make it nonlinear. So this is going to change and multiply it. Right? It will become nonlinear. Okay? So for example, for this, you cannot do a transfer function for this. Okay? You cannot do a frequency domain modeling for this. So that is the reason we will use, for something like that, we'll use general representation of state space modeling. So the general representation of state space modeling is something like this. Here, x is x is the state vector. Okay, and the dimension of this is n by 1. You understand dimension? State vector or state, this is again, in controls, vector is just a column matrix. It has no significance with the vector we discussed. It has no relation to the vector we discussed in terms of dynamics. It is not a vector quantity in physics sense. Vector here just means it is column matrix. Okay, so it's a state column matrix. It's just a column matrix consisting of state variables. All the elements of the state vector or the matrix are state variables. So if we have defined state vector here, okay, x dot is the derivative of state vector. A is the system matrix. Order is n by n. B is the input or input matrix. U is input or control vector. Y is output. C is output matrix or vector. And D is feed forward matrix vector. Okay. Yes. Yes, there is no dot. So let's look at this for a second. You understand linear independence or linear combination? Linear combination of any variables, algebraic variables, right? So if you can express S as a linear combination of algebraic variables, these kn, kn minus 1, what are these? They are constants. Only these are variables, right? If these are variables themselves, then it's not a linear combination, okay? It becomes, that's what I told you. R over R, which we wrote earlier, will become nonlinear because of it's a variable, okay? These constants, this is linear combination. So you have linear plus a combination of linear. Linear independence. What is linear independence? If you have three variables, if you can express one variable as a linear combination of the other two, then the three are not linearly independent. You see that? For example, think about solving set of two simultaneous equations. What is the condition if you have Ax plus By equal to B and Cx plus Ey equal to F, something like that? and y should be linearly independent, right? If y can be expressed as a combination of x, then you cannot solve that set of simultaneous equations. You see that, right? So here, look at linear independence in that sense. If you can express one variable as a combination of the other, then it is not linearly independent. Okay? And what is a system variable? A system variable responds to an initial condition or system output or system input, sorry. Can you tell me a system variable from what you have studied until now? Can you identify a system variable for the translational system or the electrical system? Any variable, this is important, Dion. Any variable that responds. Is the resistance a variable? It's a constant. It's a system property. It's not a variable. It's like mass. Current is a system variable. Voltage is not a system variable because it's an input. It's an input, system input. Okay? So spring constant. Huh? It's not a system variable. It's a system input. To an initial condition or system input. Right. Huh? That's what we told I just told Dion. System properties, it's not a variable, it's not changing, right? Impedance, does it change? Does it change? That's what we discussed. None of those properties change. We are assuming that those properties, LTI, when we talk about LTI, linear time invariant. That means those properties, system properties are not going to change. Okay, system variables are going to change. So current for translational system, what would be the system variable? Right. The displacement would be the system variable. Force is the system input, right? So system variable, you can talk about either displacement or you can talk about velocity, right? Or you can talk about acceleration. You see acceleration as well in there, right? So if you have an equation like mx double dot plus cx dot plus kx is equal to f, you have something like this, right? This is all these can be identified as different system variables. Huh? No, Hakim, I'm trying to tell you again and again, those are not system variables. Mass, this does not change. So what is the system variable here? Right, x is what? Displacement, right? This could also be a system variable. You see that as a system variable? You don't have to necessarily look at it as system variable, a derivative, but see if I had it like this. That changes. You have to look at it from this. any variable that changes. So this, when you apply, what is the input here? Let's say you talk about system input. System input is this one, right? This x is going to change, displacement is going to change, velocity is going to change of that system, acceleration is going to change. There has to be acceleration to see a change in velocity. There has to be change in velocity to see a displacement. So you can look at each of these as different variables, right? You can, it depends on what you're interested in here. In this system, you could be interested in velocity. Some of you may be interested in acceleration, right? Those are system variables. System variables vary with time. Keep in mind, Hakim, these are not. M, C, K are not. They are those system properties. Those don't change. We are talking about linear time invariant. Time invariant means system properties don't change. Okay? Those are not variables. State variables. What is state variables? It is just the smallest set of linearly independent system variables. So you could have a combination like this, A plus V, and we'll name it something like Z. A combination of system variables would be a state variable, okay? Linear combination. And these should be linearly independent again. State vector. So you have a few identified state variables, right? 2 or 3 or more, and you put it in the form of a column matrix. Got it? So that is a state vector. State space, this is a new concept. This means we are dealing with n-dimensional space whose axes are state variables. See, in an algebraic sense, you're dealing with a n-dimensional space. How that space is affected when the state variables get changed or get affected. Don't worry about this much, but you have to understand these. And state equations are what? State equations are a set of n simultaneous. So this is important. There are n state variables. So n simultaneous first order differential equation. Okay? When you are discussing state space, always remember it is the left hand, this is the state equation. Okay? This is the output equation. So the state equation is always do you see it as a first order differential equation? N first order differential equations. You see it, right? This will be a column matrix, right? So how many of our elements are there in that column matrix? Those many state equations. You see that? So it is, the state equations are a set of n simultaneous first order differential equations with n variables, state variables. Okay? Output equation is just the algebraic equation which expresses the system output. System output is expressed as a linear combination of state variables. So for example, if you are interested in just, so here this could be an output equation as well. Okay? So this means, or this is indicating that your output is a combination of acceleration and velocity. You're interested in acceleration and velocity. It could be just displacement, it could be two displacements, it could be just one displacement. Got it? If you're dealing with two mass system, the output could be a combination of two displacements. Okay? So these we'll develop state equation and output equation from a differential equation or from a Laplace transform in the next class. So if you are given a translational system or a or a electrical network, we'll look at how that can be transformed to a state equations. And then once you do that, you have a different set of solutions altogether now to solve those. So what did you do for Laplace transform? So think about what you did for Laplace transform. You were given, let's say, an electrical network. You wrote down the electrical network as in terms of impedances, right? And then impedances were actually Laplace transforms of each element, right? And then you developed the system input-output relationship as, or a transfer function, right? And then you solved for that transfer function. And then you did the inverse Laplace transform, and you got the response. Response is what you're really looking at. So here also we'll be looking at what the response is and how to find that response is using a different set of tools. The first one was largely, this is a lot of algebra. Okay. What you learned was ordinary differential equations was calculus. This is algebraic solutions. Okay. Here we are going to use algebraic solutions. Time domain, algebra. Time domain, differential equations. Okay. Or calculus.